So in the second video, I'm going to proceed with the rest of the topics in chapter 3. And I'm going to introduce the z-scores. This is a measure of standard deviation, but in this case, we consider z-scores as references. And let me explain how that works here. So previously, we talked about different shapes of distributions and frequencies. So they can be right skewed, and the standard deviations can represent a greater value between shapes. So to have some sort of reference or standard indication of what would be then so far from the mean, or what would be reasonable given all the parameters that we had in place, we have this as z-scores. So we got z-score, and in these z-scores, whenever it's 0, so that's in the middle here, we capture all the means. So if we say that the mean for this shape is here, all right? Let's say this is a sample mean, and it's here for this data set. So that's 1 and that's 2, and it's here. And we have different standard deviations. So let's say the standard deviation here, is for this S1 is 3, and there it could be a totally different scale, like 3000, because the scale is so high. So to be able to compare apples with bananas or with tomatoes, so to say, to be able to compare variability in totally different data sets, we need to have some sort of reference that captures them, and that is the z-score. So considering, I'm going to show you the formula for that, but we have a calculation that gives us, well, what kind of value here that is far from the mean is reflected if we take it as a z-score. So z-score shows how far this data is from the mean. So it works for all. So if we have a z-score of 1 here, for instance, it will be somewhere here. So z-score 1 or -1, that's the corresponding one, but on the negative side, it will have a corresponding value on real data. So here, if the scale here is in 3000s, or say it will be thousands around the mean, then whenever we have a z-score of 1 here, it will be some sort of thousands here, and it will be in this scale for this data set. So it's transferable. It's a standard reference that captures variability regardless of the source from where that comes, okay? So they simply, as the book says then, indicates how much a given value differs from the standard deviation, regardless of where that data comes from, okay? So when the z-score is 0, for values equal the mean, and they are positive for values above the mean, and they are negative for values below the mean. Well, if we have a value that gives us a z-score more than 3 or less than -3, we often categorize that as an outlier. And now to the right question, and that is how to calculate z-scores. Well, if it's a sample, it's simply the observation that we're calculating. So if we want to see if a certain observation is within the normal variability, meaning that it's actually less than 3 or more than -3, I mean here, of course, we're talking about z-scores, then we want to see the difference between the observation and the mean divided by the standard deviation. And that would simply give us the z-scores. So in this example, we have burgers from different places. And the question here, well, the calories that we gain when we eat Burger King's burgers, are they outliers? This is a big number. We want to make sure that, well, it's not overly greasy or something. So we want to see if this is actually something that is just a sort of, it's one data point that belongs, it's homogeneous to its data set. So what we do here is that this number, which is the observation here, minus the mean, so the mean calories that we gain from burgers in general, that would be this number in this case, the 788.4. So 1030 minus, sorry, 1230 minus 788.4 divided by the standard deviation, which is 359.5, would give us this number. So it's 1.23. That's the z-score. And we see that, well, this number is actually less than 3. So we conclude that, well, Burger King's burger are not that overly different when it comes to the calorie intake we gain when we eat them. It's just they are at highest levels, of course. So according to the empirical rule, and that's a new term that I'm actually throwing at you here, we're going to get back to it. It's just a rule that says, well, if we have a bill-shaped curve, like symmetric distribution, where you collect data and you find that almost symmetric. So you've got a number of observations on this side that is almost the same as this side. So we call that normal distribution, a bill-shaped curve. So under the area under that curve, if between z-scores -2 to +2, we embrace 95% of the data. So we say that the variability that will occur, all the data points, we at least include 95% of them between minus and 2 z-scores, and that's the empirical rule. And there's also another one for a period between, or an interval between -1 to +1, and that's the 68%. And for the z-score of 3, or between 3 and -3, the rule says that, well, we actually include 99.7% of the potential data. So any data that lies out of this interval would be considered outliers. But what if the bill-shaped curve is not in place? So what if there is skewness here or there? Here comes Chebyshev's theorem, and what this theorem says is that, well, if for everything that is beyond a z-score of 1 or less than z-score of -1, we can apply this formula to find out the z-scores regardless of the shape of the distribution of the data we have. So the implication of that, of using this formula, you don't need to actually know it, but you should know that, well, between z-scores 2 and -2, according to Chebyshev's theorem, so regardless of the shape, say that we are sure that this is not a bill-shaped curve, we can at least expect that 75% of the data would be embraced between -2 and 2, and 89% would be included between -3 and 3, and 95% would be included between a z-score of -4 and 4. So it's a little bit less than the bill-shaped curve, and that's because this one is symmetric. It's nicely put together, but this rule is a little bit sloppier. It takes into consideration different shapes, and that's why it includes less data than the bill-shaped curve. If a z-score is on the positive side, like above the mean, we call this the upper z-score, so the upper limit. And this one is called the lower limit. So if we want to know the corresponding values around an estimate, they would give us then an upper value and a lower value, all right? So coming back to this question, I want to embrace 95% of the values within +2 minus standard deviations, okay? And that is because a z-score of 2, from -2 to 2, they embrace 95% according to the empirical rule. So what we do here is that, well, this observation we start with a -1, so the -1 would be the mean minus z-score times the standard deviation. We have a 2 times 3 in this case, and that gives us 14, and 2 times 3, that gives us 26. So the upper limit would be 26, the lower limit would be 14, right? And now coming to the example that we gave earlier, so assume that we want this mail slot to be the one that receives all the types of packages. We gather data about that, and we learn that the population mean is 9-inch, and the standard deviation across different mails is 1/2 inch, right? These are just, arbitrary numbers. So if we want to embrace 99.7% of these values And we know that the distribution of such data takes the shape of a bill curve. So here the empirical rule applies. And if we want to embrace 99.7% of the potential males that we receive, then we better actually find the z-scores of 3 in this case. So that would be z-score 3. So the upper limit would be, and that's the upper limit is when the z-score is above average, so above the mean. So, and it's minus when it's less than the mean, so it's actually below the mean. So those 9 inches plus 3 times half, it will give us then 10.5 inches. And the lower limit would then be those 9 inches minus this value. So 3 times half. So if our male slot has a gap or has a height that takes into account. So if let's say that it's 10, this means 10.5 inches. So this means that we actually include more than actually 9.7, because that also takes into consideration those that are less than this number. So all the males that are less than, that has a thickness of less than 8.5 inches to this number. So we embrace more than 99.7% in this case, right? This is just a simple example. It gives you just a flavor of where we actually need z-scores. But again, all we need to do here is that z-scores represent the standard version of standard deviations. So if we want to compare data coming from different sources, then it's again z-scores. And then the empirical rule says if it takes the shape of a bill curve, then at certain scores up to 3, the intervals embrace or include a certain percentage. And Chebyshev's theorem is there just to have that sort of estimate regardless of the shape of the distribution, right? So in the first video, I showed how to make calculations to determine the mean and standard deviation for group data. So this part is already explained in terms of an example. I'm just going to conceptually go through what group data means here in this context, okay? So far, we were able to make those calculations very easily using Excel, but what if we have intervals? So we have data, we have observations that don't have just one value. What we have is observations that, well, we have a customer that came, we have 5 numbers of customers that came between 9 and 8. So what we want here to do is that to be able to create some sort of indication from such data. So this is very much explained in my example, the first video. And what we do here is that we always find the midpoint of each interval, right? And use that in our calculation. And then we use the frequency, because frequency here, all these observations represent the frequency. So each one of them is a data point, but then each data point here does not specifically refer to one value here because this is an interval, but what we do instead here is that we take the midpoint, so between 1 to 5, between 1 and 5, then we have 3 that represent the midpoint for this part. So this is explained in more detail in the first video. So moving on to the measures of relative position. And here we have 2 main measures, percentiles and quartiles. So we use them to compare the position of any value in relation to other values in the data set, okay? Let's start with percentiles. So percentiles here, they measure the approximate percentage of values in the data set that are below the value of interest. Let's take this example. So miles per gallon were recorded for a sample of 12 cars. The ranked values are shown below. What is the value of 60th percentile? So we want to know the data point under which 60% of the data are included, okay? A simple calculation here is this formula. We have P, that's the percentiles. We have 60, so a 60, and 60 divided by 100, that's the 60%. And N represents 12 because we have 12 observations. So 60% of a 12 observation returns 7.2. We need to round up this always. So we go to the 8th observation. So we start with 1, 2, 3, and of course this is ranked from the lowest to the highest value. So we go from 1 to 8, and that 8th value is the one that represents 60th percentile. Okay, 60th percentile. So the answer to this question is that, well, the 60th percentile is 31.1 mile per gallon. Percentiles in Excel are calculated so easily. Well, all you need to do here is that you type this formula, percentile.xc. The array here is the data set, basically that's the range of the data, and k represent the number, the fraction interest. So if it's the 60th, you have to write it's 0.6, so 50% basically. If it's 20th, it has to be 2 in this case, right? It is the percentile of interest and it's between 0 to 1. 1 is 100%. This is just a note here that Excel uses a slightly different technique to calculate percentiles. That has to do with the rounding up that we did. So it's a little bit more accurate because we try to round up this. Excel does not do that. It gives more accurate number. That's fine. Coming to the percentile rank. So you want to know if a specific value or observation, data point, well, what is the rank of this considering the percentile? It has a rank from a percentile perspective. It identifies the percentile of a particular value within a data set. So formula for that is the number of values below x. So how many values do we have below that value that we are interested in finding the percentile rank for, plus half divided by the total number of values. And that's times 100. Let's have an example here. So in this case, we are reversing the question. So the question here is, what is the percentile rank for the car with 35.8 mpg, right? So the number of values below x is 9. So we have this number, we have this value, we see that, well, we actually have 9 values or 9 observations below this number, okay? Plus half, and that's part of the equation, divided by the total number, which is 12, times 100, and that just give us the number, not the percentage. And we find this as 79%, which is the 79th as a percentile rank. Okay, so this is just helpful if you want to see, well, we have scores from students. Well, what's the ranking of this specific score, and thus this specific student among the other students? And we find from that where this student is he actually within the top, meaning that those who have higher percentile ranks. And now we move to quartiles, and quartiles are in principle percentiles, but with specific percentiles. So quartile 1 is actually 25th percentile. Quartile 2 is 50th percentile. So quartiles actually partition or split the ranked data into quarters. So we have first quartile after 25th, or basically 20% of the data. That's the value that splits the data set. And then after another quarter, meaning the second quartile or quartile 2, and then quartile 3 for 27th percentile, and that's it. So we have 3 percentiles. Otherwise, we have 100% of the data, and that's quartile 4, but we don't use it. Most of the time, we have only these 3. So Q1, Q2, Q3. So these are percentiles, just the fact that they has specific numbers. 25th, that's the first quarter, then half of the data, and that is 50th, and then 27th. So in this example, we want to find the first quartile. So we want to see where the percentile, 25th percentile, basically. Okay, so having that in mind, using the same formula we used to calculate percentiles, we have 25%, and we have the total number of values here is 11. So we get this as 2.75. So we round up that. So we know that it's in the third position. So it's 13. That is Q1. That's number 13 here. And again, we have another formula for that in Excel. So we're all set with it. We can use it to answer all the questions. So now we know how to calculate quartiles and percentiles both manually and using Excel. So the number of values between quartile 3 and 1 is called interquartile range. So interquartile range describes the middle 50% of a range. So the data that is between basically the 75th and the 25th percentile. So this number, this measure is very important when we plot. We do a plot now, and that's called a box and whiskers plot, or simply whiskers plot. So when we use whiskers plot, we sort of identify where the limits of our data is and where from which limits we should consider any observation an outlier. Okay, so we use interquartile to capture that. And here's an example, and that's what I called what I told you earlier about box and whisker plots. So a box and whisker plot is a graphical display showing the relative position of the three quartiles. So we have first quartile, third quartile, and we get the median here. Okay, so we see that, and the maximum and minimum values here, see this dotted line or dashed line? So we calculate the length of that using the interquartile range. After those limits, we consider any value an outlier. So below that, it's an outlier. Above this is an outlier. So how do we actually construct this plot? It's very simple. We need to find the third quartile, median, first quartile, and interquartile range. These are all numbers that we can calculate. So how do we find the upper and lower limit, as we see in this picture? It's simply after, this is the quartile 3. Sorry, yeah, that's the quartile 3. That is, it's the 75th percentile. This is it. So this limit plus 1.5 times the interquartile range, meaning the third quartile minus the quartile 3 minus the quartile 1. So 3, this number plus 1.5 times this number minus this number. And the lower limit, it just goes into the opposite direction. So minus 1.5 times the interquartile range, basically this number minus this number, right? So beyond these limits, any value is considered an outlier, right? So to construct a box and whiskers plot, first determine the three quartiles, then draw a horizontal number line that spans the length of the data values, so all the data values. So if we have the highest value as this number, for instance, if we say that this is 9 and the lowest one is point something, so we draw a line that embraces all these values with a scale. And then we draw a box above the number line extending from Q1 to Q3. So a box from Q1 to Q3. And then median should be within that, right? And that's Q2. So median, for those who are wondering, Q2 is always the median, okay? And that's actually the definition of median. Median is the data point that splits the data set into 50%. Then we extend that. This is the interquartile range, 1.5 of that. So 1.5 times interquartile range, 1.5, and then to the other direction, right? So once we draw this, all other observations that we find are considered outliers. Here's an example. So after we rank this data, and this is the national park visitors, we see that the number of visitors in million for this national park, Yellowstone in Wyoming, it's the one that represent 75th percentile, meaning the quartile 3, and this one represent the quartile 1, all right? So this national park is then the median. This value is the median. So from there, we can calculate the inner quartile range, and that is this value minus this value. So 4 minus 2, we'll get this number, 1.89. And the inner quartile range, this one, will be multiplied by 1.5, 1.5 in different directions. Okay, so we'll find this point and then draw a dashed line towards the box, the whiskers plot, and then to the from the box then to the positive direction by 7 points. Okay, so as we see here, 7.095, that's the highest limit. So we see from there that we have an outlier here with a very high number of visitors. So this would affect our analytics. So any conclusion that we build based on studying the data of these places would be affected that. So we consider this a special case from that perspective. Practically, we would treat this differently because it probably has some sort of characteristics that may make it different or sort of different from the other observations, right? So that's an outlier in this case. This is how we decided that, right? So we also call this the 5-number summary. So the 5-number summary consists of the minimum value, first quartile, second quartile, that's the median, and the third quartile, and the maximum value, right? So finally, we have 3.6. This is the last topic in this chapter, and it is about a completely different types of measures, and that these are the measures of association. So here, what we do is that we draw a line. This is a new topic. We have two data sets that represent two variables, and we want to know if they are related or associated in any way. This is how we diagnose many of the treatments that we have today in medical sectors, for instance. We see if after consuming something, if there's a change in some sort of levels to have some sort of conclusions about the association here. So in this basic introduction, I will describe two measures basically, sample covariance and a sample correlation coefficient. Okay, let's get started with it. So this one is actually derived from this one. So we have the variance and correlation coefficient is a corresponding measure to the standard deviation. We have a variance, standard deviation, the same thing we have here, covariance and correlation coefficient. So it's the formula here is a little bit more complex than what we've seen so far. But to be able to see if this is a sample covariance, and that is actually covariance, not variance, you will see here that there are two symbols here, meaning that these are two variables. So there is an S here, and that's for the variance for the sample. But instead of having one variable, we have two variables here. And that's where you say that it's a covariance. It's not just a variance, okay? And in principle, the formula is similar to the variance. Instead of having it to be just the distances between observations and the sample mean, that was squared, but since we are now multiplying two different distances, so distance for the first variable and then the second variable, we don't need to do that square because the minus sign will be got rid of using this operation, right? So we're gonna have the summation of all these operations divided by the number of observations minus 1 because this is a sample. Well, then, given that we have this covariance, we can basically derive the correlation coefficient, and that's the one that we most of the time rely on. So what we do here is that we take that covariance that we found and that basically divided by the standard deviation of the first variable alone or separately and multiplied by the standard deviation of the other variable. It's so simple. It's probably a little bit more complicated to calculate, especially if we do it manually. So the sample correlation denoted by Rxy, and these are the two variables, indicates both the strength and direction of the linear relationship between the independent and dependent variable. So when we have R and in minus, that means that the higher the higher the levels of the first variable, the lower the other one. So they go in opposite directions. If it's positive, then the relationship is in the same direction. So the higher of this, the higher the level of this value, the higher the level of the other value. And then the strength here. So R is a measure from 0 to 100%. So it's the strongest possible is that we have a perfectly correlated relationship, which is something only in theory when we have that's basically a math function. So if we have 1 here, that's a perfect correlation, a positive correlation that is strong because that's basically the highest correlation coefficient. But then if we have 0, that means we have no correlation whatsoever. How would that be in practice? So the correlation for 1, we're going to see that x and y have linear relationship and it's perfect. So there is no, they all reflect the same changes here. When R has minus, then we have high values when x has low values, and it goes in the opposite direction. And then the strength of the relationship start to take a dip if we see that this linearity loses some shape. I mean, I would say in real world that 0.6 is even very high or very strong relationship. The book says something different, but I would say that we get so excited when we find a relationship that shows like a 40% in our project. So six is sometimes considered unrealistic. So -4, that's also an interesting. So we see -4, oh, that's a celebration time for us. All right, and this is how you calculate them for a sample. So covariance for a sample and correlation for a sample, it will be just Corel, and covariance for a population, right? That's using Excel. And that makes your life much, much easier. So I'm going to give you an example here, and that's example going to be exactly the same example that you'll have for a quiz on Tuesday. It will have different values, right? The first quiz will have a question with some data like this, and it will ask you about what sort of from these data, what would the following be? So we have a mean, a median. So these simple questions here. We have here an average. That's the straight up formula, and then you have median, mode, and range. So range here is basically calculated this way if it's a long range. So we have a max. Max finds the highest number in a range, and min finds the lowest one. So max minus min will give us the range, even if you think that you can do that straight away. I mean, you probably don't need it from that perspective, but it just doesn't hurt to know this. If you have a very large data set, it would help you do that very quickly. And then you have the sample variance, and that's var s, sample standard deviation, that std dot s, and then the coefficient of variation, and that's the one that we ended with during our class on Thursday. And then we have the z-score. That's a question about a certain z-score. And in this case, it's the one that corresponds 27, right? And from there, what we want to do is do that calculation. So it will be according to manual calculation. We have 1, 2, 3, 4, 5, 6, 7. So we got 7 data points. So it's going to be 70% times 7. So that will give us the 5th place. 1, 2, 3, 4, 5. So it's actually 40 for this number. For this example, it's 64. So that would be then 46, I'm sorry, 46. And we're going to do this, we're going to follow, these numbers are not the right ones, so we're going to do that again using the percentile calculation, the manual one. Second example would be an example like this. We're going to get values similar to those. We have 2 variables, and then number of sales. We want to see if there is a correlation between the number of sales representatives and the number of cars sold, right? So we have those numbers for the different weeks here, week 1, 2, 3, 4, 5, 6. And we have the number of cars sold for that period. So we calculate the sample mean here, the sample mean for the number of cars sold, and we find the difference between the sample mean and the representatives, the first for this column and for that column. And from there, we do calculations. So it will be this value times this value plus this value times this value, and so on. And all the result of that all will be divided by number of observations, so 6. Since this is a sample, it will be then 6 minus 1. Okay, so that would give us the covariance. And then the correlation would be this number divided by the standard deviation of x times the standard deviation of y. So that's basically in line with the equation. Or we can do, what we can do here is that we use the Excel formula. That is, in this case, I use this round just to show all the answers in a rounded shape, but you can also use the covariance one. Covariance for the sample, it would give you the answer straight up. So you have the range for the first variable and the range for the second variable, and then you get the covariance. For the correlation, it's the same. You use the first range for the range for of the first variable and the range of the second variable. Right? So see you on Tuesday, and prepared for this quiz. You'll have around 20 minutes or a little bit more to finish it. Right? Good luck and see you on Tuesday.